to our second foyer into foyer. We're going to start doing more stuff. There we go. It's our second one. Moving in. Let's actually do some calculus now. So here's your definition from your book. Tangent line to the curve y equals f of x at the point a comma f of a. Just two numbers. Just at some frickin' point. What's the slope of the tangent? Oh, shit. Is the line through P with slope. Wow. Provided the limit exists. What's that mean? What the hell is this thing even saying? M is equal to the limit as x tends towards a. X is getting closer and closer to a. So x is getting closer and closer to a. So I wonder what happens here. I think maybe it turns into a frickin' zero? Weird. It's like that shit happens constantly with limits. I'm always dividing by zero and trying to figure out what the hell to do with it. As your x gets closer to that a, what do you think? Do you think that function might get closer to its the value when you plug that shit in? I don't know. I don't know if you see it, but really what we're going to do is we're going to create this again. We're going to create some 0 over 0. We're going to get shit close together. We're going to get our x values close together, and we're going to get our y values close together. That's what's happening. We're going to find the slope. If that doesn't make sense, don't trip. We're good. And we can also say it's this. The limit is x2 gets closer to x1 of y2 minus y1 over x2 minus x1. Remember your slope formula? Remember that thing? It's just saying if you get your x values really freaking close together, what's the slope going to turn into? Because that's that tangent line thing we're showing you before. It's like if you get that shit close. So, I don't know. Let's look at 3 graphs. Let's just look at 3. And they're all the same graph. But we're going to play a game with our new notation. So I'm going to get that out of here for right now. All right. Here, we'll look at our first. Hey, there's A. There's A, and then it's the number, whatever number. So if that A was 1, and maybe f of A is 2, so you'd be at 1 comma 2. It's just a number. Now let's put in an x value just to the right of it. I'm just going to put in something and say, that shit's x. Right here. And go, all right. And I'm going to make a line right across here. Now, do you think that does a good job of mimicking the tangent line? The tangent. Let me get a little tangent line going on for you here. What do we think? Think a tangent line? What? Maybe like this? Maybe like that? Maybe get a tangent line that looks kind of like that. Would that be? Maybe something different to that. Just smaller. What do you think? A tangent line maybe like that. That might be okay. That might kind of like right where it would just kiss. Like would be the slope of you going down a slide. So I don't think that's a very good estimation, right? The slope of this thing, this point right there, that point at x comma f of x. I don't think that's a very good one. All right, let's put the x closer. How about we put the x like here? Hey, that's better. We're getting closer to it, and now we're like. There's a little line. We're just trying to match the slopes. We're just trying to get the slope of the secant line to match the slope of the tangent line. I'm going to pull out the ruler again. Let's check it out. It should be the same slope. I just don't mess with this thing. I don't have to do it again. I'm like, oh, that doesn't look too bad, huh? That looks pretty good. I doubt it's perfect, though. Now, to our eyes, it looks really freaking close, but that might just be because of where I put it. That was actually a very poor choice of spots that I put that. But we continue on. Now what happens if we would do something like this and we put x right, let's put x right here. You know what I mean? We're going to put x right there. Right there, that dot. Wow, it's looking pretty freaking close. Pull out the ruler again, let's find out. Like, oh, that might be pretty good. Man, we can't even draw the line because the shit's so close, you can't even see it in there. But you kind of catch the point that if we make the secant line get closer and closer and closer together, the limit, eventually it's just going to turn into the tangent line. So that's what's happening up here. We're saying, dude, as your x values get closer and closer, whatever that a might be, the function, the y value is going to get closer to the fucking... Ooh, I didn't say that. And I'm not re-recording this. Gosh dang, if my mom was listening. Don't tell my mom. I do my best. Do my best. Okay. Yeah. As your x values get closer together, your y values get closer together. And it's going to create some sort of slope. And the magic of limits is actually going to show us the slope of the tangent line by doing this. So let's just jump into an example. I was going to use another one just in case. I think I made it so. I don't know. Let's see if we can't find. Oh shit. Oh my gosh. Let's find an equation of the tangent line. To the parabola. I'm basically stealing this shit straight from your book. You can look at this. We all kind of use the same stuff. I'm going to change it up a little bit. Y equals x squared, but they call it y equals x squared. You know, let's call it f of x equals x squared. At the point, let's call it 2, 4. 2, 4. So we want to find an equation of the tangent line to the parabola. F of x is equal to x squared at the point 2, 4. All right. So we introduce this way of finding the slope of the tangent line at the beginning, and I do one. And I'm going to change it up on you in the next video, but follow this. This is a very valid method. You could be doing all of your problems like this if you like it better, but I'm going to kind of switch it up on you and do it a little bit different after this one, because this only solves for things at the given point. The way we're going to be able to do it in a little while is we're going to be able to solve for any value of x. So this is just a technique to find it at the particular point. Let's go. So let's just start defining things, because we're going to need to use this formula here first to find the slope. Just to find the slope, we're going to find the slope of the tangent line. That's going to be the limit as x tends towards a of f of x minus f of a all over x minus a. When you're stuck and you're not sure what to do, play a game with me. Just start defining your variables. Be like, hey, I found f of x. We can just put x squared right in there. I found x. It's sitting right here. That one's fine. But you got to figure out, what the heck's a? What do you think a might be? Maybe the x value in that point? This a, this a, this a. They're all the same thing. That's the same a. And you know what happens if you were to take that a? I think that number's 2. What happens when you plug 2 into x squared? What number do you get? Heck yeah. You get 4. That's f of 2. So f of 2 is equal to 4. That's saying when you plug in x into your function, it pops out 4. All right. Enough of that. I shouldn't be doing so much algebra with you. I should be teaching you calculus. Sorry, y'all, for those that are really good with your algebra already. Oh gosh, I don't need an algebra lesson. Shut up, dude. So I'll shut up. Let's go. We're going to say the limit as x tends towards 2. That's going to be 2. We just write in our f of x. Oh no, we don't do shit with f of x's. All we do is we plug in what they equal. Don't do stuff. If you're ever trying to do something to an f of x, probably wrong. That would suck. And then minus, what's our f of a? Oh, that's our f of a. It's right here. That's our f of 2. That's our 2. That's how we would write that. So f of 2, f of a, is equal to 4 all over x minus, and our a value was 2. I think we've seen this problem before. I think we've done a limit like this. So now we're just going to hustle. It's clearly that we're going to use a difference of squares up top. Cancel, cancel, cancel. And we're going to get that the limit as x tends towards 2 of x plus 2 is going to be equal to 2 plus 2, which equals 4. Now this is the slope of our tangent line. Now maybe I write it in like this. The slope of the tangent is equal to 4. So we found the slope. That's the hard part of these problems. Finding the slope is the tough part. So you just actually found, if you're following along and you're doing this work with me, you're seeing how we can find the instantaneous rate of change of any function at any point if we want to know. We've solved the slope problem now. This is something that would kept Newton away from all this shit. The idea of a limit. This is what held back Leibniz and everyone else that was chasing after calculus. This is the slope problem. We can start solving freaking everything. we're going to learn how we truly graph. Maybe not the stuff we've done in the past where we've very much bypassed and that are handheld. We're going to be able to, when we get into chapter 4 or into all our theorems, man, you're going to see how long it takes to just create one graph. It's going to be good stuff. Okay, so we're not done. Let's finish it because we still need to write the equation of the tangent line. What we just found was the slope of the tangent line. But doesn't an equation look something like this? That's the equation of the line, and we already know its slope. We just have to find, we just got to find that y-intercept. But I don't think we should do it that way. I don't like this one. This is the y equals mx plus b, the slope-intercept form, and it's dope. It's a great equation. But in calculus, maybe we want to lean a little heavier on this. The point-slope form. Y minus y1 is equal to the slope times x minus x1. Let's lean a little heavier here because we're going to start to see it written notationally quite different. Quite different. Because this is not that tough to solve if you think about it this way, that we have a slope and we're given the point at the beginning. So all you have to do is just plug in your numbers. There's your x1, y1 up here. And there's your frickin' slope hanging out over there. Everything in blue is where that shit's going to go. So that's not the hard part. The hard part is going to be able to read the notation when we're actually starting to write it like this. F of x minus f of a is equal to m times x minus a. That's what we're writing. We're getting more fancy. We're not using frickin' y values as much. And you can use y, it's fine, but that's where we're moving to. This is where by the end of the class, I hope that you're comfortable with that. But I'm gonna get rid of this now. Just kind of a precursor of the things to come. So let's stick with this. I think this is sufficient. So let's plug it in. Y minus, and it's y1, so that's 4. Is equal to the slope of our tangent line, which is 4 times x minus, and then that's the 2. And there we are. Now, so many of you are going to be like, I can't help it. I have to keep going. And if your homework needs it that way, your homework needs it that way. For me on a test, leave that. Leave that. One of my things that kills me is when I see students do this, and then they screw up the distribution, and then they get the wrong answer because it's been beaten in their head that y equals mx plus b is the only acceptable equation of a line. It's not. This serves a great purpose. Weird. It's called point slope. It's great when you have a point and the slope, because it's called point slope. So anytime you have a point and a slope, use this one. Don't use y equals mx plus b. And if you have to, because your teacher told you, I'm not sure why they told you had to do this every time. Okay, there you go. Maybe it's easier for you to graph this way. Y is equal to 4x minus 4. So we found an equation of a line, and I'm about to be done babbling. I'm about there. I know we're 13 minutes in. Holy crap, I should shut up. So if you have some sort of graph that's coming in, your x squared, and we're at 2, we're saying that the equation of this said line, it's just going to kiss right off of it. We can say that this is y is equal to 4x minus 4. Notice it's something that's sloping up at about 4. I have it down here, maybe negative 4. So it's some sort of line. And that's what we're doing each time. We're going to start using the equation of a tangent line to mimic what the kind of like the slope, in big quotes, of the curve is going to be at that point. This is a game. This is something I'm going to put on your frickin' final. I'm going to ask you to find the equations of tangent lines or other random stuff. It's going to be on your first test. It's a big thing. So the slope of the tangent line is the instantaneous rate of change of a curve at a point. But we'll talk more about that as we go. Sorry about such a long video.